Hey folks, so here is our video. We're getting started looking at friction. So I'm going to make the assumption that you have a little bit of background in this, that you have studied it a little bit in physics before, and hopefully we'll draw on some of our practical life experience as well. So first of all, in picture A right here, we can see we've got a block that has a weight W, and we know that the block is sitting on the surface, and if the block isn't sinking through the surface, there must be a force equal and opposite. So N in this case must be equal to W, and we call it N because it's the normal force, yeah? And because that force N will always be normal to that surface. So if we now apply a force P, and we try and push our block to the right, we are going to find that unless this is a frictionless contact surface here, there's going to be a friction force that develops here. Now, if we just push a little bit, if P is very small, then F is more than likely going to equal P and cancel it out. But as we increase P, F is actually going to reach a limit, and at that point the block will then start to move. Yeah. So if we take a look in this little graph here on the right, this is kind of what we have. Yeah. So our force F, the more we increase that force P, then F will increase, and this whole time our object is in equilibrium, yeah, during this whole area. But eventually that kind of maxes out, we reach a maximum value, and then the block starts to move. And once the block actually gets going, it takes a slightly less force to actually keep it going, and our friction force now will be constant, and we will move, and we'll continue to move and accelerate to the right. So in this little line here, we're going to use this phrase a lot, impending motion. This is where we get to the point where right at this point, when F equals its maximum value, and we've increased P so that P and the maximum value of F are actually equal at this point, we're just right about at that impending motion point. So what it basically means is, like, if we increase P by even the tiniest amount, then we'll overcome that friction force and it will start to move. Yeah. So as I say, hopefully you've had some experience of this. None of this is new, and we're going to talk about the way that we calculate that friction force. You may be familiar, is we have what we call a coefficient of friction, and we use the Greek letter mu, and that's multiplied by the normal force. So this is our coefficient of friction. Now we have two types of friction. We have what we call static friction, and we use a little subscript mus, and that's basically what we have going on in this area when we're in equilibrium and the thing isn't moving, right? So not moving, static. Once we overcome that maximum force of static friction, then it starts to move, and we have what we call kinetic friction. So we also have, in this instance, so that would be our Fm there. Our Fk, our force of kinetic friction, would be mu, and we use a little subscript k. So that's our kinetic friction, and that's our. So we have a coefficient of static friction, and we have a coefficient of kinetic friction, in the same way, which is this mu k. Okay. So one of the things we can do, because if we look at this, we've got this force N and this force F, and F and M are related. We can see here, right? F is equal to mu N, which is kind of an interesting little piece of information that we'll use here in just a second. So if we take a look at this first box right here, here we're in a situation where we've got P and W, we've got a force P applied pushing down. There's actually nothing in the horizontal direction, so there's no motion, so there's going to be no friction, right? But we're going to have a normal force that's going to oppose P and W, and that's going to be our total reaction there, N. In this instance, now we have P that actually has a horizontal component, so we're going to actually get friction. Now let me draw this out over here, and I'll show you kind of what we're doing here. So we've got a normal force, we've got our weight, which, let me try and draw that. Yep, we've got our weight, we've got a normal force, we're going to have our friction. And let's just draw the x component of P. But we know that F is equal to mu N. So if we draw a little triangle here, if we take that force N and that force F, so this is mu N and this is N, so we can combine these two vectors to make an overall reaction force R. And if we look at this angle in here, we'll call it phi. Phi is going to be, let me try that again, the inverse tangent of the opposite over adjacent, yeah? So the inverse tangent of mu N over N, which obviously is the inverse tangent of those ends cancel, yeah? So we can say that phi is equal to the inverse tangent of our coefficient of friction. Okay, so that's what we've got. If you notice this, we've got a single reaction force, and hopefully you can see this on the video. It's a little fuzzy, but phi, here in this case, we can look at the angle of this reaction force, and if phi is less than phi s, so phi s is what we're going to call, let me make a little space over here, our angle of static friction. So what we're saying here is that this angle here is actually our phi s, which is the maximum angle that this reaction force can have right here before we've basically maxed out our static friction. Yeah. So if this angle here, if this angle phi is less than phi s, then what that means is that the friction force is less than our coefficient of static friction times our normal force. So what it means is our friction force still has a little bit of room to grow. Yeah. So we're still in that static range. If we're in the situation here where phi is equal to phi s, right? So that means our friction force has actually reached its maximum point. So on our graph, we're right here. That's when we have what we call motion impending. So we're right at the point where it's about to move. And then if we reach this point where now we have, if we're in a situation where phi is equal to phi k, so now phi k basically is what we had before, but it's the inverse tangent of our kinetic coefficient of friction. So that's our angle of kinetic friction. And if we're there and Fk is less than Px, then that means we do have motion, we have an unbalanced force, yeah? And that friction can't increase any further because we've maxed out, we're on our kinetic friction. So a couple of final points just to finish up is that we always were in a situation where friction is going to oppose any kind of motion. So if we apply a force this way, the friction is going to come this way. If we have a block on a slope and it's going to slide down, we have the weight, which could resolve into two components here. So this here will be, this component of the weight will be equal to our normal force. This component of the weight is going to be our unbalanced force down the slope. So the block's going to tend to want to slide, so the friction is going to push back up the slope that way. Yeah. So friction will always oppose motion. So we'll stop this video there and start taking a look at some examples.